Welcome to this explainer. Today we're going to unpack the fascinating, totally invisible technology that's literally running our modern world. To put things into perspective, right out of the gate, the computer that guided Apollo 11 to the moon had just 4 kilobytes of RAM. Today, your smart fridge has millions of times more computing power than that. Wild, right? So if you've ever stopped to look at the smart devices around you and wondered how a tiny little chip makes them so incredibly intelligent, you are definitely in the right place. We're pulling straight from the latest industry guides today to decode the hidden digital backbone of our daily lives.
Think about this for a second. How does your washing machine know exactly when to stop spinning? Or consider how a car's anti-lock braking system reacts in mere milliseconds to prevent a crash on a rainy highway. We're not talking about general-purpose computers here, like your laptop that's juggling 100 different apps at once. No, these are highly specific, dedicated systems built to do one job and do it extremely reliably.
And that brings us to the absolute core of today's topic, embedded systems engineering. It's the rigorous discipline of designing, building, and seamlessly integrating hardware and software to bring these dedicated computing systems to life.
All right, here is our roadmap for today. 1. The invisible digital backbone. 2. Hardware meets software. 3. How embedded systems work. 4. Embedded versus software engineering. 5. Building a lucrative career. And 6. The future of embedded tech. Let's get right into it.
Section 1. The invisible digital backbone.
Basically, almost every physical object around us is becoming smart. In healthcare, embedded systems power life-saving devices like pacemakers and ECG monitors, where precision is, quite literally, a matter of life and death. Out on the road, modern vehicles use dozens of embedded controllers to manage everything from the engine to advanced driver assistance systems. From the smart appliances sitting in your kitchen to complex industrial robotics and the entire aerospace ecosystem. Honestly, none of this connected, automated world would even exist without embedded engineering.
Section 2. Hardware meets software.
I absolutely love this description from our source material. Embedded engineers are the full-stack professionals of the physical world. It perfectly hits the nail on the head. You can't just hide in the code, and you can't just solder circuits all day. You have to deeply understand how the low-level firmware orchestrates the physical sensors and actuators in real time.
And this is absolutely crucial because these engineers operate under incredibly strict physical constraints. Imagine writing code where every single byte matters. It's essentially survival mode for software. A poorly optimized piece of firmware could drain a smartwatch battery in hours instead of days. So you're constantly doing this balancing act, dealing with limited memory, tight power consumption, and the absolute non-negotiable need for instantaneous, real-time responses. Moving on to Section 3, How Embedded Systems Work.
So how do we actually get from a concept to a physical device sitting in your hand? Well, it's a very sequential journey. It kicks off with hardware design, selecting microprocessors and laying out circuit boards. Then comes firmware development, which is writing that low-level C or C++ code to act as the device's brain. Next up is software integration, connecting the device to networks. Because these systems often run highly critical things like cars or medical labs, the testing and validation phase is incredibly rigorous. And finally, deployment, which, by the way, is exactly how your smart devices receive those magic over-the-air firmware updates.
Section 4. Embedded versus software engineering. Let's contrast this with a role you might already be super familiar with. Traditional software engineers generally focus on high-level application logic, user interfaces, and back-end systems using languages like Java or Python. They usually have vast computing resources at their disposal and honestly don't need to know much about what the underlying hardware is doing. Embedded engineers, on the other hand, live exactly at that low-level intersection of hardware and firmware. For them, deep hardware knowledge isn't a nice-to-have, it's essential, and they rely on languages that give them precise memory control, like C and C++. If we compare this to a closely related role, like an IoT engineer, the nuances become even clearer. While an embedded systems engineer focuses super deeply on device-level hardware design and control, an IoT engineer essentially bridges that device to the internet. They focus a bit more on end-to-end connected systems, utilizing Python and cloud SDKs to make sure the embedded device communicates perfectly with cloud servers. But make no mistake, the foundation of both of these roles fundamentally relies on embedded principles.
All right, Section 5, Building a Lucrative Career.
Okay, let's talk numbers, because the financial growth here is incredibly compelling, particularly in booming global hubs like India. Salaries scale up really impressively based on experience. Freshers might start out between 3.5 and 6 lakhs per annum, but within just 3 to 5 years, mid-level engineers can double that, easily jumping into the 6 to 12 lakh range. Seniors command between 12 and 22 lakhs, and lead architects with niche, specialized expertise, they are scaling well past 40 lakhs per annum. But to command those top-tier salaries, your skills have to level up progressively. It's a journey. You start by mastering the fundamentals: basic electronics, digital logic, and embedded C. In the intermediate stage, you get hands-on with ARM microcontrollers and real-time operating systems. As you get more advanced, you pivot into embedded Linux and complex IoT integration. And at the expert level, you are architecting entire systems and pushing cutting-edge artificial intelligence right to the edge of the network.
And honestly, one of the biggest advantages of this career path is the massive cross-industry demand. You are not boxed into a single sector here. You have total flexibility. You could work at semiconductor giants like Qualcomm or NVIDIA, automotive leaders pushing autonomous driving like Bosch and Continental, major tech service providers like Tata Elxsi, or consumer electronics titans like Samsung and LG. Your skills are universally needed across the board.
And finally, Section 6, the future of embedded tech.
Zooming out for a second, on a macro level, robust electronics ecosystems are rapidly expanding and transforming global tech hubs into massive centers for research and development. This is heavily driven by strong government initiatives, things like the Make in India campaign and Production-Linked Incentive or PLI schemes for semiconductors. These initiatives are actively enticing global tech giants to set up dedicated massive R&D centers.
Technologically speaking, the future is incredibly exciting. We're seeing the rise of TinyML, literally squeezing machine learning models onto tiny microcontrollers. Edge computing is processing data instantly on site for ultra-low latency rather than waiting for it to bounce back from the cloud. Add in the evolution of autonomous vehicles requiring advanced sensor fusion, the rise of Industry 4.0 smart factories, and the seamless integration of 5G connectivity. And well, the demand for these systems is just skyrocketing.
So here's the bottom line. These systems quietly but powerfully run our increasingly connected reality. The physical world is rapidly becoming entirely digital, and it urgently requires engineers who can fluently speak the language of both. So as this Industry 4.0 revolution really takes off, where are you going to fit in? Thanks so much for joining this explainer, and we'll catch you next time.